show, and we can jump right into it. So today's case is going to be on hypothesis testing, but it's going to be more in an analytical way. So you would, if you have seen the Jupyter Notebook of the case before, you would see most of our today's teaching will be done through looking at different mini apps that C1 nicely built. So there won't be too much coding in so what you would just run with me. I know some of you might be having problems. So what you should typically do is in your terminal. So you should go into your folder, case 5, intro to hypothesis testing. And then run the share requirement .text. Do the pip install -r requirements.txt, and then go back to the Jupyter Case Notebook and then run the first cell, importing our applet. So it might take a while, so don't feel something is wrong. If it's not loading, or if you're seeing some error for you, that's okay. That happens, because again, almost 1,000 of us are trying to accessing the server at the same time, and then it might be slowing it down. So if you cannot find it, it should be in week 5, and then there should be a case called Intro to Hypothesis Testing. And Ricardo, I do watch a little bit of Latin series. Like my favorite is La Casa de Papel. So my favorite character is Nairobi. So yeah, sometimes when there are shows on Netflix in Spanish, I would always watch it in Spanish, because that's I do want to learn Spanish, because I think Latin America is a great continent, great place, very friendly people. I've been to Mexico and Peru, and I loved the food and the people there. So Colombia would definitely be on my next destination. So I really do hope to come to Colombia. So so a quick question asking where do I live. I am in Toronto right now, because the latitude is just much higher than Colombia. So in the summer we get very long daylight, so that's why you still see sunlight in my screen. But so yeah. So okay. So let's before we dive into the case, I also just wanted to make a disclaimer. So I came from physics research training, so the statistics that I was taught, or I was required to learn, if you were coming from like a formal mathematical statistics background, you might be you might find out that I might be missing some assumptions. I would try my best to cover them, but then this case is meant to give you all a very practical understanding of the concepts in terms of hypothesis testing, and how do we apply these concepts when we are looking at data, doing hands-on work. So if you're still having problems with the notebook while if it's not loading or there were some problems, please get in touch with your TAs or Oscar. I'm sure they would be happy to help. So let's dive into it. So the business context of today's case is we are in a data analytics team, and we were asked to conduct an assessment for protected forests in California. So our job is to determine which species of the trees in our protected forest area have heights that are substantially different from the average height across California. So in that case, or in other words, we want to find out what specific species of trees that are known to have a very different height from most of the trees in California. So the data set that we got, there were 18 species of tree data, and then each species had 100 trees. And then the table that we have, there are 5 columns. The first one is a unique tree identifier, so we don't have to pay too much attention to this. The next one is the height of the tree in feet, so this one we do care about. And then the next one is something called a site index. It's a concept specific to the field of forestry. So they have some method to normalize the height of the tree according to the age. So it's like you are comparing a bunch of 8 years old students versus 18 years old students. But then of course they are very different in age, so we expect their heights would be quite different, right? So this index is like a normalized factor to account for that age difference. And then the last two would be the tree species common name and scientific name. So we wouldn't care about these at the end, until the end. So so the flow of the case, we will be explain a lot of the statistics concepts before we actually do our analysis. That's because we wanted to understand. We will go through quite a number of new terms, like that many of you might have not heard before. Diego, an applet is just like a mini app. So cool. So let's dive into it. So in our data set, there were almost like 400,000 trees. And then the mean height of all these trees are 57 feet, or about 17.5 meters. So we defined something called the population mean of the tree height to be this number, 57.35 feet. Okay. So in Greek letters, we love using Greek letters to represent some variables. So it's just a general statistics practice that we typically call the mean to be mu. So the mean of the height of the trees, or we call it the mu here, would be 57 feet. And you can see a histogram so of how the height of the trees distribute. So yeah, Andres, yes, that's absolutely fair point. That since the distribution is skewed, so typically when we deal with this type of distribution, we often use the median as a measure as well. So we were using the mean for the following statistical concepts, teaching purposes. You will see it right away. So if we think about the distribution of the population mean, and then we try to map it to something called probability distribution function, or something called PDF. not the Adobe documents that you typically open on your computer. Here, whenever I say PDF, I am meaning probability distribution function. Okay, so just remember this term in your mind as well, because this is going to be repeated many times in today's case. Okay, so if we look at the PDF of this trees population, since we know the mean already, it would behave like a delta function. So what is a delta function? If you have heard it before, it's like a line, basically, but then it only has one value. So it's like all 0, 0, 0, 0, 0, and then at 57.35, you have that spike, and then say at 57.36, you go back to 0, 0, 0 again. Okay, so since it's a PDF and all probability distribution function, we required that their area to be normalized to 1. So you would see here the we only know the mean is 57.35, and that's the only number we know. So that's what we would, if we were asked to do a plot of the height of the trees, since we don't have all these functions here, like all the different tree, if we don't have these heights, but we only know the mean, this would be something that we tell people. But of course, we all know that's not realistic, right? So because to have them this, because this is like and already we know the mean, and then it would be if we were asked to tell like what's the complete distribution of the trees, like it would be almost impossible for us to tell, because it's almost impossible for all the trees in California to be measured in height, and then we have all the data to it. Nope. But then what we can do is we can sample that distribution, right? So for example, you can there's a table, say let's say sample 20 trees, and then compute the average, and we would get some number as well. We expect it would be close to 57.5. but it might not be exactly 57.5 because in our case, 57.5 was like was like a pre-given value to us that we were going to use for the hypothesis testing later on. But then in real life, we sample as many as we can and then calculate the mean and then use that number as the number that we reference. So here, exercise 2 is our first applet. So if we all run the cell and then click the link, you would go into an applet like this. So here you would see the first option that we can choose is the sample size. In statistics we usually call it n, as in the total number of samples available. And then here we are asking Python to draw a number of random sampling populations for us. So let's say we ask it to just randomly draw 20 trees out of 100 trees, and then these would be the height. And you would see a population mean mu. Let's see if we have a value here. Yep, 50. So this is the population mean mu. That's our reference value that we'll always be referencing throughout the case. But then if we just take an average of all these trees here and take a mean of that, you wouldn't get 57.35. Okay, you're getting something like 59.8. So we're getting close. Okay, but we wouldn't get exactly the same. And then what you should play around to make sure you remember this sampling concept is as we move the number of draws to a smaller number, you typically would see a number, the red, the mean of the sample mean would show up further away from the population mean. Okay, if we increase the number of draws by a lot, say let's go to 60, we would then see that the sample mean is getting much closer to the underlying population mean. So this is what we call the sampling is we are getting to the underlying mean value of our data. So William is asking, is there any rule of thumb to select the subsample size? Exactly, it depends on the actual data. Viviana, we will go through central limit theorem in just a second, so bear with me for just a second. So in this app, you would also see a green line here. That's something called a distribution, or like I mentioned again, our friend PDF. So this green curve is an approximation of the PDF that we could extract from the samples, not the exact underlying PDF, but just by the samples, right? And a lot of there's something called the special bell-shaped distribution called the T distribution. Can be can be used to describe what we are sampling very well. Okay, so let's close this app and run this one as well. So here you would see basically the same app, just like before, but then here there is an extra blue curve here called the T distribution PDF. Okay. So what for when I was curious about different statistical distribution, I often go to first take a look at Wikipedia and then look at other statistic textbooks. But then to understand what the T distribution is, you can imagine it as just the same as a normal distribution or something that we call a Gaussian distribution, but with a fatter tails on both ends. So here the blue curve here is our normal distribution curve with a mean of 0 and a certain width. Okay, so maybe the width can be somewhere around, say, 1. Yeah, and then the T distribution it looks very similar, but it's slightly different. So it still has this symmetric bell shape, but we have the two tails on the end that are the values are slightly bigger. Okay, and then there is also something called the degrees of freedom. So let's see, let's go back up again. The degrees of freedom is typically used to describe how big is your sample size, how many data points do you sample, and then as the degrees of freedom goes bigger and bigger, the shape of the T distribution gets closer and closer to the normal distribution. Here you'd see from this example, if we go from 1, 2, 3, and then 5, 10, 30, when we get to 30, the T distribution curve almost looks exactly the same like a normal distribution curve. That's something called the central limit theorem. It basically states that any PDF, if the degrees of freedom is big enough, the shape of that PDF will always converge back to the normal distribution. So that's what the central limit theorem means. So another important concept that that's related to hypothesis testing is something called p-values. So a p-value is basically a measure that how likely if you repeat the same measurement for a certain number of times, how likely are you gonna get a number or get a result bigger or more significant? You can require it to be smaller, of course. How likely it is that you're gonna get a result different from what you know previously. Okay, so you're given a certain data point, and you try to sample it, right? You trying to get a sense of what the underlying distribution looks like, and the p-value basically tells you how likely that you're gonna get a very different result. So keep this idea in mind, and we will combine all these concepts in the following exercises. So so far we have learned the t distribution, right? And we have the sample mean doesn't doesn't exactly follow the underlying PDF, but instead it follows a t distribution. So we also covered p-values. So let's try the next exercise. So exercise 3. Then this is our an example to show you would be working. So let's start with something like this. Okay. Am I still freezing? Okay, okay. If that happens, just let me know. Can you all hear me okay? Let me try to put the headphones closer closer to my mouth. Okay, great, thank you. So again, we have the same sample size, right? So this xi value is something that we use as a reference, right? So you remember what was our mean, underlying mean height of the trees? Yeah, around 57, exactly. Luis and Nicholas, Alfonso, Valencia. Yep, great. So if we pick an xi value of, say, around, let's try to pick 57. Okay, so if we try to pick a value of 57 to be our xi, we would expect that half the trees would have heights larger than 57, and half of the trees with height smaller than 57, right? So in that case, we would say our p-value is around 0.5. That means if we were to draw a sample from our sample size, draw a number, half of the time that we will get something bigger than 57, and half of the time we'll get something smaller than 57, right? So that's how you can interpret or understand the concept of p-values. Yep, exactly. And p would be something like 0.5. Okay. And then as we go higher and higher, let's go to say 70. If we require our xi to be 70 feet, then you would see basically 99.9% of the time, if we select another tree and compare its height to our threshold selected here, 70 feet, 99.9% of the time we'll get a number lower than 70 feet. Right. So so here we say the p-value for 70 feet is 0.001. That means it's extremely unlikely that we pick a tree from our data set that it's gonna give us a height with 70 feet or taller. Okay, extremely unlikely, because the mean height of all the trees that we have, the underlying true value is about 57 feet. Same case for if we wanted to, if we really lower our threshold, say go to 30 feet, you would see almost any tree that we select are going to be taller than 30 feet, because our mean is somewhere here, 57. And then the p-value here, that we get a value taller than 30 feet would be 1. So p-values, of course, would always be a number range from 0 to 1. And then if we are just using the mean as the value, then we would get something like very close to 0.5. Okay, so that's why all these distribution and p-values are useful when we don't, in real world, when we don't have access to the underlying truth. We can only rely on sampling as many data points as possible. So so that's why these terms are used as a very standardized language as statistics to describe how special our measurement result is. We can put it that way. So Matteo, p-value is the probability of getting a sample mean equal to the number chosen, right? So yes and no. So you should think about it as the probability of getting the next sample or next measurement larger or smaller to the number chosen. It will make more sense as we go through the next exercise. Okay, so so let's see. If we take one sample size Yep. So if we only draw one one sample from the population, then it would, let's see, the t distribution is the distribution of the mean of the sample. So yeah, you can think of it as that way. So the t distribution, when you do a certain number of sampling, then and you try to plot a histogram, then you would get a distribution that follows the shape of the t distribution. And then is the t distribution specific for this problem's data, or can we use it anytime we want to do the sampling distribution? So the t distribution is not specific to this problem's data. Whenever you are dealing with a sampling problem, we will be looking into that. So a t distribution is typically what we use to do a first hypothesis testing. So you can apply it to many other problems. But then as the sample size gets larger and larger, you would come across something called Z or Z distribution as well. That's when the number of samples get really big. So here, let's say in this plot, in this exercise 4.1, to help you better understand what the p-values and what intuition you should have when you see someone quotes a p-value to you. Let's go through this exercise and hopefully you all get a much better sense. Okay, so we have this underlying PDF, and then let's say we do two sampling. Let's say we do sampling A, say select 10 trees, calculate the sample mean, and then we select another 10 trees and calculate the sample means, and the values A and B are the sample means that we get. Is it more likely to observe A or greater or B or greater given our sampling distribution, given our underlying blue distribution? Great, you guys are understanding it. You guys are having the right intuition. 8 or greater is more likely, right? Because remember, a very useful property of the PDF is if you do an integration of the PDF, if you do an indefinite integration, then you should get an area of 1. That's the mathematical definition of PDF. But if you do indefinite integration with bounds, then what you get would be the probability of getting a measurement within that range. So here you would see if we try to integrate from the value A here to infinity, say, or just maybe to 70, that's not a big difference. And then if we compare the integration from B to infinity, or say B to 70, the value of that area integration of A would be bigger than that area integration of B. So that means it's more likely to if we do entry from our data set, it's more likely to have the height of the tree falls into that range between A to infinity or B to infinity, then B to infinity. Um, so now you can probably answer this without any difficulties as well, right? So if we compare the sample mean B to another sample mean C, so is it even possible to observe C as a sample mean? We would all be answering no, right? So because C is already a very, very unlikely outcome when we try to measure if we try to measure the mean of a bunch of sample trees. So if we try to integrate this PDF curve from C to infinity, compare it to integrating this curve from B to infinity, like the value difference is going to be huge. So that means it's going to be much more likely to get a sample mean B than a sample mean C. Right. So after some warm-up exercises and an introduction to p-values, let's see if okay, breaking voice again. So let me quickly repeat 4.2. So if we now have a sample mean B compared to sample mean C, to observe a sample mean C is a lot more unlikely than observing a sample mean B, because integrating this area to under this PDF curve is much smaller than integrating this part this part of the PDF curve. Okay, so now we can sort of move into hypothesis testing. Finally, our topic of tonight. So so let's see. There is a very useful term that we always use in statistics to describe whether we should treat a set of measurements seriously or not. We always call it statistically significant or not. We can always use hypothesis testing to tell whether our measurement is statistically significant or not. Okay, so let's say we measure again a bunch of trees, like draw a sample again, and then we get the sample mean to be 56 feet, and we know that this value sort of makes sense because it's very close to our underlying mean of 57.35. But then if we draw another sample, say, and get a sample mean of say 66 feet or 76 feet, then we know it sort of doesn't make sense. It sort of makes us doubt our measurement because we know that the underlying mean is 57 feet. And if we draw a sample and calculate a sample mean to be 66 or 76 feet, it's so far away from the mean that it makes us sort of doubt the measurements that we made, right? So so to mathematically tell whether that sample mean value makes sense or not, the whole process is called hypothesis testing. So An hypothesis is basically an educated guess that whether the mean or whatever value that we measure makes sense or not. So the first step in hypothesis testing is defining the null hypothesis. In statistics, we usually denote it as H0. So you can imagine the term null hypothesis means a very conservative claim, or we call it the status quo. So so the conservative hypothesis would be, say, the mu1 that we get from a random sampling. The sample mean would be equal to the underlying value. Here would be 57.35. Then, but it's not enough that we only have the null hypothesis. We always need to have an alternative hypothesis, right? And that's Francisco, you're asking the exact right question. How much the difference between mu and x is statistical significant? We're gonna get right into that. Okay, so but you're thinking in the right direction. So the hypothesis testing, it exactly uses the p-value to tell us how much the difference between mu and x is statistical significant. So we're going to get into that right away. Okay, so but then so right just before I was saying we have this very conservative null hypothesis, and then we have the alternative hypothesis. So the alternative hypothesis is sort of like a challenge to the conservative hypothesis. Okay, but then we have to perform some tests, right? That's exactly why this is called hypothesis testing. So it's like the judicial system, innocent until proven guilty. So we do this in a way that we always assume the null hypothesis is true until we find some statistically significant evidence that suggests that the null hypothesis is wrong. Okay. So Dorian is asking, what if we don't have mu? How could it be calculated? Right. So that's a very good question. In principle, we wouldn't be able to do it because we need to have, or we can use the value that after, say, we sample as many trees as we can to be the mu. That can also work, but then for the hypothesis testing, we always have to assume the conservative null hypothesis value to be true, and then test the alternative hypothesis, see if it has enough evidence to tell us that our original null hypothesis is wrong. Okay. So, but then it's important to remember this approach is not perfect. Okay. Even if we don't find enough evidence to prove that the null hypothesis is wrong, it can still turn out to be wrong. Okay, so it's analogous to like a trial in the court. Say the judge couldn't find enough evidence to suggest that person or that robber is guilty, that doesn't mean he is not. So it can still be the case that our conservative hypothesis can still be wrong. Okay, but to formalize this process, we define an alternative hypothesis. We usually call it H1 or HA. I typically like to use H0 versus H1 because A can easily be confused with alpha, which is another important quantity that we are going to be talking about in the second half of the case. So let's use H0 to be the conservative null hypothesis, and then H1 to be the alternative hypothesis. So there are a few cases that we can define these alternative hypotheses. So it can be another idea that challenge this mu equals mu1. Of course, we can suggest an alternative hypothesis or another idea that mu does not equal to mu1. Or you can also suggest say mu, we're challenging your original null hypothesis that mu is bigger than mu1 or mu is smaller than mu1. So there are several different ways that we can suggest these alternative hypotheses. But for this case, let's just go with the last idea. Say our sample mean is actually bigger than the original mean. So that means our alternative hypothesis is we are suggesting this idea that the trees that we have, the average height of these trees are actually taller than the underlying mean. Okay. So let's take a look at the same plot from the previous exercise, right? So we know that mu is our underlying mean, and then let's say we believe that our trees, if we after certain sampling, let's say we believe our trees, the mean height of our trees is actually value B. Okay. But then if someone is saying the average height of the trees is value C, then of course we probably wouldn't believe him, right? If someone is coming to say the average height of the trees that we got is actually value B, we would immediately find this person saying, or the alternative hypothesis, more trustworthy, right? Then how would you come up with a more objective criterion to determine whether that that average height of the trees are statistically different from mu or not? So let's say a reasonable way to do that, since we are just all of these talking were very theoretical, and subjective and not objective. So one good way to do that is to define a threshold on the x-axis, and then whatever that threshold is, if that's if we get a sample mean that is above that threshold, then we can say it's statistically significant or significantly different from the underlying population mean. If it's not, then we wouldn't say it's significantly different. So how do we determine this value? I would want to Christian, exactly. Amber Heard is innocent. X1 is guilty. Yep, exactly. So so this is a question that I want you all to think about for a minute, as we are approaching like the 1 hour mark. I would suggest let's all take a break. Okay, stand up, stretch our legs, get some water, and while we try to think about what is a reasonable way to tell whether this setting threshold method is good, or in other words, if you were asked to set a threshold, what value would you pick? What p-value would you pick such that anything, say a value c shows up in your measurement, then you would immediately say, oh, wow, this is significant. While say if your measurement comes out to be value b, then okay, you would immediately say, oh, this is not very significant, right? So as you would all be thinking about, so I should probably set the threshold somewhere between, say, B and C, so maybe somewhere 65, 66, 67, but this picking process is, it's kind of arbitrary. So let's take a break for 5 minutes, and then after the break we'll come back and I'll do some more explanation about the threshold selection process. Monica, can you pause the recording?
Yes, of course. Just a second.
Yeah, so we will come back at 8:05 Colombian time. And meanwhile, I will play some music.
That's awesome. Thank you. So just a second, we are going to pause the recording. All yours, Sammy.
Yeah. So I see some very good answers already.
caña. No habrá manera, mi rayo de luna, que tú te vayas.
So just a sec while we switch the share screen, I did see a few very good answers. Juan Camilo said 0.95. Yeah, that's that's great. Uh, six. Hey, Monica, can you all hear me?
Okay, Sammy, we are set. I'm sorry, my bad, my bad. I was sharing some.
No, no, no. It's all good, Oscar. Thank you so much. Okay, now we're back. Like I was saying, a lot of you gave some pretty good answers, right? So before the break, I was suggesting we can probably choose some threshold between B and C, say 65 feet, and call it a critical value. Okay, so let's say our critical value is 65 feet, and then if we measure a sample mean to be a value B, which is say 62, below 65, then we can say it is not statistically significant. But if we measure something like 69, like value C here, that is bigger than 65, then we can say, since it's above the critical value threshold that we chose, then we can claim it to be significant. But then the problem is this process seems rather arbitrary, right? We didn't say, we didn't mention any specific reason why we like this number 65. Why it's not 64? Why not 66? Why do we prefer 65? Right? So to really standardize this process, a very good way to use is the p-value. Okay, as a number of you also mentioned in the live chat just before the break or during the break, this is a very important concept. So I want you to pay attention a little bit more after the break and get this, take away this important concept to you, right? So we're always going to have a distribution in our measurements in real life, right? But then every time when we want to select a critical value threshold to tell whether a measurement result is statistically significant or not, it's the standardized way to do it would be using the p-value. In that case, we wouldn't have to worry about the exact sample distribution, whether it's whether it's a normal distribution or T distribution or say Poisson distribution, things like that. If we use the p-value, we can always find a corresponding point on that distribution curve that corresponds to the p-value threshold that we set. Okay, that's something we call significant levels, and we typically use alpha to represent the significance level. Like in a lot of social sciences or biology, or some other sciences as well. We typically say a result is significant when the p-value is smaller than 0.05, or the significance level is 0.05. Okay, so a good way to think about why we chose this as a very common practice for alpha or significance level threshold is, you can think about it as this alpha represents how many times you should repeat your measurement or you should repeat your experiment until you get consistent results that you can trust what you measure. Okay, so 0.05, that means if you do a 1 over alpha, you would get what it means by the number of experiments that you should repeat until you establish some confidence in the measurements that you made. So for example, 0.05, that means if you repeat the same experiment by 20 times and you still see consistent results, okay, that means in the sciences community, that means you probably did a good job in terms of carrying out your measurements or carrying out your experiments. That, okay, we are going to trust your results if you get if your results is consistent with an alpha of 0.05. And then here you also say in natural sciences popular standard is 0.01. So 0.01, that means it's a much stricter requirement, because that means you have to repeat the experiment, repeat the measurement 100 times, and only if you get consistent results, then your measurement would be considered trustworthy. Actually, instead, I can we can look up in particle physics. That's where my background training was in. We were only allowed to claim this is an evidence for a new particle, or claim this measurement to be a discovery if P is 0.000003. That's also something what we call 5 sigma. So what it means by 5 sigma is, in your normal distribution, sigma usually means how wide is your normal distribution. And in normal distribution or Gaussian distribution, 1 sigma always means 68% of your samples are within your 1 sigma away from the mean. Okay, and then if we go to 2 sigma, that percentage goes to 95%. So a lot of your fellows already answered during the break, saying, say, 95% would be a good threshold to set. Like, so here the 95% of this curve, if we use that as a threshold, then it's probably strict enough. If we go to 3 sigma, that would mean 99.7%. So, so I also remember some of you answered 3 sigma or p equals 0.003 to be as the significance level, right? So that means if you're it's also equivalent if you tell people, say, okay, this study I'm requesting a significance level of 3 sigma, that means p is 0.003, and also that's also equivalent to say I'm only trusting the results of my experiment unless I repeat it 300 times and I still get consistent results. So does this make sense so far? This is a very important language and also a very important concept in statistics, in hypothesis testing, and also in reporting results. That's the common language that people use to report on the significance of the results of your measurement. So yep. So let's move on to the next exercise. Exercise 6. Here we have another very nice applet. Okay. Right. So let's see. Yep. Again, we have, say, a certain sample size, right? Here, then we are requiring a certain significance level alpha, right? Here, this is, let's set it to 0.05, like we were explaining. So this would be the corresponding value of alpha equals 0.05 would be 63.9 feet. So that means if we get a measurement of value B, which is, say, 62, that means we are not seeing a statistically significant result. And in hypothesis testing terms or language, we say we are failed to reject the null hypothesis. Okay, so why this is critical? Because we always say we are failed to reject, but we're not accepting, because the population mean can still be a wrong value. This is just we're just saying that the measurements that we did, say we came up with a sample mean of 62 feet, does not have enough evidence to tell us that the actual population mean of all our trees, the mean height is 57. Okay, but then if we measure something to the value C like 69, then the story would be very different. In this case, since it's the mean is above that critical value for alpha equals 0.05, we say this measurement provides enough evidence for us to reject the null hypothesis, right? So it might sound negative to you, but then when we say our results are significant enough to reject the null hypothesis, that usually means there is something interesting that we should go look deeper and find out why something interesting is happening. And in physics or science or research world, that means you'd probably get to publish a paper. So remember this terminology, like it might sound negative to you, say rejecting the null hypothesis, but it actually means something interesting is going on. Fail to reject, that would mean, oh, this measurement is consistent with it's consistent within the fluctuations of what we expect. So it's probably there's nothing interesting going on. Yeah. Okay, so here's 6.2, fill in the blank. So I can give you two options. The bigger or the smaller the alpha, the more conservative your test, and therefore the more difficult it is to reject the null hypothesis. And after all the explaining that I did, I hope you all get the answer, right? The answer would be the smaller the alpha, the more conservative your test would be. Okay, so let's go back to the app, and then let's see if we go to like really small alpha. Let's say, let's see, 0.01. Okay, yeah, so we can only work at 0.01. Right, the critical value for alpha to be 0.01 is 66.7 feet. So if we really push alpha to be really small, then even if we get a measurement like 69 to C, we would almost be calling the C measurement to be fail to reject. All right, so if we can move the significance level alpha to say 0.003 or 0.001, then the null hypothesis for sample mean C would also change to fail to reject. But then if we use a very loose significance level, like say 0.5, that means no matter if we measure B or C to be our sample mean, we would still reject the null hypothesis. But then we all know this wouldn't be a good significance level to use, because that means it would be very easy for us to claim that, oh, the height measurements of our trees are telling us enough evidence that the trees are taller than the average. So we typically, that's why we typically set it to say 0.05. Okay, so now we can compare alpha and p-value. So since you sort of have seen quite a number of examples, so a rule of thumb to remember or to quote your results of your hypothesis testing is if the p-value that you get is smaller than alpha, right? That means you get something really interesting, and you can reject the null hypothesis. I always like to use the word interesting versus null, because that means your scientists get to stay employed and do more experiments in the lab to find out more interesting discoveries. So exactly, David. Yeah, that yay moment when your p-value is less than alpha. Yep. So right. If we get a p-value, if we didn't discover something interesting. Okay. So okay, am I back? Great. Okay, thank you. So quick question. Suppose you conducted a t-test or a hypothesis testing with significance level of alpha to be 0.01, and you get a p-value to be 0.02. Do you reject the null hypothesis, or you fail to reject the null hypothesis? Fail. Yep, exactly. Yep, you fail to reject the null hypothesis. Good, very good. You're always been thinking of the case where whether we get a sample mean greater than the actual population mean. But we can do this the other way. The logic is exactly the same. So except you would define your p-value to be getting a value smaller than the expected mean, or you can even do a two-tailed t-test. So in this case, you would just you're not asking whether the sample mean is bigger or smaller than the population mean. You're just asking whether these two mean values are statistically different. Okay, so this is actually going to be if you work on say a gender pay gap data science project. A lot of the time you have some salary data of men versus women, and then you would do a t-test to you can do a t-test in two ways. You can do a t-test to check whether the men's salary data, the mean is higher or larger than the mean of the women's salary data set, or if you have say a same data set of two groups of women with say different demographic or educational background, then you would be just doing a t-test to check whether, if we're doing a two-tailed test, what we would do is we would divide the alpha by 2 and also divide the p-value by 2. So if the sample mean falls outside the range of either critical or significance level or the threshold, then the test will give you p-values that would indicate that you should reject the null hypothesis. Okay. So Guillermo, it's you should be careful when also Francisco, when you are talking about fail to reject versus accept, because sometimes fail to reject means you still don't know whether the null hypothesis is true. It's just indicating that the measurement that you got, the results that you got, are very different from your expectation. Okay, it can be a positive thing, it can be a negative thing. So just be careful. You so is no, because the p-value that you required is also divided by 2. So let me did I freeze, or am I back? Okay, so let me explain it one more time. So the two-tailed t-test, the major difference of that from a one-tailed t-test is two-tailed t-test, you're basically using it to tell whether the mean values of two samples, if they are significantly different or not. But then if it's one-tailed t-test, then it would probably mean you are testing whether that sample mean is bigger or smaller than the other sample mean. So now, after we have explained all these different concepts, like we have covered p-values, t-test, significance level, etc., etc., we can now finally go to our forestry survey and look at some of the numbers. So it would be much easier for us to understand exactly with real data. That would be, it would help a lot. So like I said, we are using this site index to correct the height of the trees, and then we are carrying out the t-test for all of our 18 species, and then the null hypothesis for all our tests would be the mean height of the trees that in our data set equals to the mean height of the trees that we know in California, which is also, again, that number, 57 feet. And then the alternative hypothesis is that the mean height of this particular species is not the same. It's not the same as the mean height of all the trees in California. So here is the resulting p-values of all of our 18 species. Right, you see this column. These are all our p-values. Which species exhibit a statistically significant difference at alpha equals 0.05? Right, so how are these p-values calculated is, so you would take all the trees of this particular species, say blue oak, get the average height. That would be our sample mean, right? And then we use that value to compute the p-values of where that average height sit relative to that blue distribution that we have here. Okay, so how is it calculated? You would typically integrate, so you get the sample, you get the sample mean here. You integrate from the sample mean to infinity, and then the ratio of the area above that sample mean divided by the total area of the PDF curve, which is 1. That would be your p-value. So Jose very quickly pointed out that these are the few species that show significant difference at alpha equals 0.05. So let's take a closer look at these 7 species. Okay, so we have lodgepole pine, Jeffrey pine, blue oak, and western white pine. Like, these are all they have p-values of, say, 0.01, 0.02, And then white fir and tan oak, they have smaller p-values, like 0.001 and 0.007. And then redwood has the smallest p-value, 0.000185. Okay, so these p-values correspond to how far away their sample mean is away from the population mean. Okay, so for example, if you see redwood, or in other words, sequoia, you would see the sample mean is 101 feet. That's a lot higher. That's a lot higher than the population mean. And then the other species that if you compare their sample mean and the population mean, they're not that different. So the p-values is actually is a very good indicator to calculate the so okay, let me check the questions. Okay, so I was just slightly worried about the internet. If I'm sounding okay, then I will continue. So yep. Daniel is asking, is there any Python function to calculate p-value? Yes, definitely. I can post more result. I can post more resources. I believe some of your fellows are also posting. Yep, exactly. scipy.stats would be the package to go. So you call the different already in place PDF, and you can give it in Python. You can give it the expected mean value, and then your measured value, and then SciPy stats would give you the p-value. So okay, so here we got to our last exercise. So if we look at the table above here, many of the difference seems very small. If we do a sample mean of all these different trees and compare them to the population mean, a lot of these differences would be within 1 feet or 2 feet. Okay. Why these differences seem to be very small is because the difference of 1 feet, the percentage of 1 feet over the sample mean height of these trees, which are all like at least 50, 60, even 90, 100. So these are all 1 to 2% different. So that's why we say that many of the above differences seem to be very small. So that means it's possible that we might be setting the significance level too strict. Okay, and as some of you were suggesting in the live chat, this is known as the multiple comparisons problem. That we are basically doing enough sampling such that we get a p-value that is significant, right? So you can imagine this as playing lottery, say. If you play the same game or same lottery enough, enough times, there will always be one time that you win, right? So this is what the multiple comparisons problem means. So if we keep doing the sampling, we would increase the false positive rate. That means we can use another example to look at it. So let's look at COVID testing. So we all know, say, the rapid antigen test of COVID is not 100% accurate, right? So let's say if you originally don't have COVID, and then you just keep doing this rapid antigen testing, keep providing your sample to do the antigen test. Eventually you will get to a point that you finally meet a rapid antigen test that is going to give you a positive result. So that's what it means. So as you do more and more sampling, eventually you're going to come across a false positive. In that case, then if you just, based on that, and reject the null hypothesis, then you wouldn't be doing the right thing. So to fix this problem is of course to reduce the significance level, right? So a very famous strategy is called the Bonferroni correction. So it's basically suggesting that if we are doing this, repeating this measurement 18 times, then we should divide the significance level alpha by 18. So in this case, the alpha we were using, which was 0.05 divided by 18, we would get 0.0027. In this case, only the redwood tree here and the white fir would show us these two species have a significant difference between the sample mean and the population mean. So here, the first one, the sample mean is 1.2 feet bigger than the population mean, and then the redwood tree here, the sample mean is 5 feet taller than the population mean. So after doing this correction, then we would be selecting a more reasonable threshold, saying that, okay, these are the only interesting, only 2 of 18 species have interesting measurements that we should look into it, rather than 7 out of 18. Because if you have 18 species of trees, and then it turns out if you did tests or measurements and came out 7 species out of 18, is telling you that, oh, you have something statistically significant that you should look into it. It wouldn't make it that interesting to look into, right? But then if you change the significance level to be 0.0027 using the Bonferroni correction, then you only get 2 species out of 18 that are suggesting there is something potentially interesting going on that you should take a deeper look into it, right? So Yep. So this is the before we get to the end, I would also want to cover what it means by type 1 error. So when we say false positive, we also call it type 1 error. So this concept mainly came from medical treatment or medical diagnosis. So let's say if you go to a hospital and take an X-ray and your doctors look at it, the doctors have some ability to tell whether say you have cancer or not, let's say. But then even the best of the best doctors make mistakes, right? So basically here what it means is for TP means true positive. That means say if your X-ray comes back to and your doctor said, oh, it's bad news for you, it looks like you have cancer, and indeed you have, that would mean a true positive. And then the true negative, it means if your doctors take a look at your X-ray and the doctors tell you, oh, it looks like you're clean, you don't have any problems, you don't have any cancers, then and you actually do not, that means it's a true negative. Okay. But then what we typically interested in is, say, is the cases in between. So these would be problematic, right? When your X-ray doesn't seem to be showing you have cancer, but the doctors somehow, for some reason, believe that your X-ray results is showing you have cancers, that would mean this is a false positive case, right? And then the other way around, when it from the X-ray looks like you have cancers, but then you were actually clean, there might be some problems in the camera that causing your image to look like you have cancer, but when you actually do not, that means this case would be a false negative. Okay. And then the type 1 error here means false positive. That's typically what in statistics we call it. And then for false negative, we call it type 2 error. So depends on the disease you have. We might care more about type 1 error, or we might care more about type 2 error. So for example, the case of COVID, we would care false negative or type 2 error more, because if we cannot test someone to be we fail to test someone who is positive, and that person has a negative result, that person would go around and potentially keep spreading COVID to other people very quickly, right? So that's a bad thing that we don't want to see happening, right? So but if it's just a flu, okay, even if it's false positive, then probably not such a big deal, right? So right, sensitivity of a test is not exactly the same as p-value, but yep. But then this is just I wanted to introduce the false positive, what it means, what typically means by type 1 and type 2 error. So yep. So we basically that's sort of the end of our case. We explain many new statistical concepts, hypothesis testing, p-values, alpha, t-test. So it's definitely normal if you feel confused. Many of your fellows posted a lot more useful resources to help understand the concepts covered in this case. So so if you feel confused or feel lost somewhere, feel free to reach out to me, feel free to reach out to your TA, feel free to watch the videos again. And I also, when I was learning all these concepts, I also didn't get it the first time, so it's definitely fine. So the most important is you get exposed to the standard language in statistics. How people use p-values they were getting. All these would help you understand when you're doing data analysis, all these terminology and language help tell your data story to people who are seeing your work for the first time. Am I back? Right. Okay. Yeah. So the takeaway message this case is so now you've seen what hypothesis testing is and what language is or what terminologies are used to describe the results of the hypothesis testing. So namely the alpha and the p-value. And we also covered at the end, we also covered a little bit of what it means by false positive and how we should be adjusting what means to be a reasonable significance level, depending on how many times we're repeating our experiments or measurements. And it's important for you to remember that if we torture the data enough, like it will confess. So that means if you keep doing more and more sampling, but then if you keep the same significance level, eventually you would get something statistically significant. But then that's not the right thing to do because you were just playing the lottery game again and again. There should be a trade-off that you should understand that behind the sampling, you should also adjust your significance level as well. So yep. So I think that's all. I was gonna cover for today. Thank you all again for having me. Let me at least turn on my camera again so I can see all your faces again. And yeah, really thank you so much for sacrificing your evening time to come and learn new concepts. It's okay if you don't get it the first time. I didn't get it the first time. If I were seeing these new languages the first time, I wouldn't understand it 100% as well. Keep reading more and more resources and keep asking questions, and eventually you'll get there.
Thank you so much, Sammy. Muchas gracias.
And